Hi everyone. So before going deeper into the topic of graph-based recommender systems, just a few words about Kernix. We are 15 years old web agency, which nowadays is composed of a digital factory which designs websites, and it's coupled to a data lab in which Joseph and I are currently working. So this allows us to handle upstream phases such as studies or POCs, but also downstream phases with industrializations of our solutions. As regards the data lab, our field of expertise is quite wide. It spans from data pipelines to data visualizations, and one of our core business has become the building of customized recommender systems for various clients. So usually, when we have to build recommender systems, we usually use graph databases as building blocks of those engines. So for those who don't know those kind of databases, in those databases, the data is stored as nodes. In one given database, you can have different labels which represent different types of data stored in the node. So here, for example, you have a sample of the movie lens dataset which was introduced in the last talk. In green, you can see one type of label, and in the red, it's another type of label. In fact, the green one is a user, and the red ones are movies that were rated by this user. The data are stored in the nodes in the form of properties, and on top of that, the relationship between data is explicitly materialized in the graph by edges. So here, for example, the fact that this user rated all those movies is materialized by an edge going from the user to the movie. Those databases have their own query language, which allow to perform what we call graph traversals, because those queries actually they correspond to looking for a specific path in the graph. So why do we build graph-oriented recommender systems? As you can see, those databases allow to gather heterogeneous data in the same structure, and on top of that, it allows to explicitly take advantage of the relationships between data, which can be useful for the purpose of recommendation. I will show you later that this recommender systems allow to can be meaningful for humans. That is to say that it's prone to interpretation. Usually, the implementation is rather easy because computing a recommendation corresponds to one single query to the database. And to finish, the execution is often fast because, in particular, it doesn't need any training to perform recommendations. So to be a bit more concrete, I will show you an example. We built a recommender system for a website that was developed by our data factory. The website is Hobby Street. So the aim is to facilitate connections between craftsmen who propose workshops and private individuals who sign up at these workshops. So on the craftsman side, they propose workshops and they can link those workshops to different categories. So for example, do-it-yourself, cooking, art, etc. They can also fix the dates and prices of the workshops. And on the other hand, the individuals that can sign up at those workshops, but also can follow workshops or categories that they are interested in. Among the specifications that we have had from our clients, the website had to handle registrations, plannings, payments, and also propose customized suggestions to the private individuals. So this was the part of the job that we did at the data lab. Here you can see the structure of the graph we used to build our recommender system. You can see that there are 5 different types of nodes. So on one side you have the craftsmen who propose workshops. Each workshop can be related to several categories, and also each workshop has several sessions, one session being an instance of a workshop with given date and price. On the other side you have users who can sign up at sessions, but also follow craftsmen or categories or workshops they are interested in, to keep being informed about those categories and workshops. So, to perform our recommendations, we choose to mix 3 complementary strategies. I will explain at the end why those strategies are complementary. And each of these strategies corresponds to a single query to the database, as I said before. So the first strategy is the one we call category-based. It consists in retrieving all the categories that are linked to the user up to a degree 3. So for example, we will retrieve all the categories that the user has directly followed, but also all the categories that are linked to workshops that the user followed. Then, among this subset of categories, we will recommend to the user the most popular workshops. The second strategy is the one that is based on the comparison of the text describing the workshops. As a prerequisite to this strategy, we use latent semantic analysis to attribute a similarity score to each pair of workshops that is in our database. And this similarity score is then materialized in the graph database by adding a new type of edges between workshops with as property the similarity score. And then this strategy only consists in recommending to the user workshops which are the most similar ones actually to the workshops that are linked to the user. And the last strategy is the one that we call user-based or similar user-based. So this consists in finding a subset of users who are similar to user 1, who is the user to which we want to recommend workshops. This subset of similar users is defined as the subset of users who have the greatest number of workshops in common with user 1. And then we recommend to user 1 the workshops which are the most popular, but only among this subset of similar users. So why did I say that those strategies are complementary? For example, if I focus on the first strategy, you can see that this one, for example, if the user never is not interested in cooking, or at least if he didn't follow or participated in any cooking workshop, we will never propose to him cooking workshops. So there is no serendipity in this strategy. But on the contrary, in this one, this can bring new things and workshops that the user wouldn't have found maybe by himself. So now I will let Joseph show you another example.
Okay, thanks. So we just saw recommender system based on user. So now I will show you a case more focused on content. And this case is Cambly. So what is Cambly? It's a bit hard to explain like this, so I will quote Wikipedia. It's kind of multi-format media company producing its own mix of culture, art, and news. Okay, so when you go to this site, in fact, what you can see is posts about news and arts, and you can read it and navigate on the site. And one thing important is that it became one of the first websites to put social media at the heart of their strategy. That is to say, you have also all the ratings or the likes of Facebook and Twitter shares close to the article. So the issue of Combini was that they have a really high bounce rate. That is to say, the user were just viewing a post and going back just afterward. So there is no real travel in the website. So the solution we recommend them is to build a recommender system by using proper recommendation. We will ease the user experience, and what we achieve is to help them down, reduce this bounce rate to 50%. So this is the context. And how did we succeed this? This is the data we had in input, if you want. So we have, in the graph database, all these entities as nodes. There are posts in several languages, because there are several websites, in fact. And you can see the numbers of nodes aside the posts. So this is one kind of node. And you have also the author and the categories of the posts. So these are all the entities that are in the graph. And for all the posts, you have also a list of properties, especially the published dates, the Facebook count and Twitter count, and also a boost that I will explain after. So this is the basic data we had in input, and what we did is to construct a simple graph of this data to link them. That is to say, from one post we build relationship between this post and other posts through the sharing of categories or authors, and we also implement the semantic analysis to build the similarity relationship between the content of the articles. So this is the graph, the really simple graph we built for Combini, and the recommendation will be performed by a simple query to this graph, taking into account all the relationships, the semantic similarities, the number of categories the post have in common, the number of authors in common, but also their own properties, that is to say the freshness of the article, the social counts, and finally a manual boost that will help Combini to help article to bubble up into the recommendation list when they want to perform, for example, specific campaigns, marketing campaigns. So this is all the ingredients for the recommendation. So once again, this recommendation is based on a single graph queries for all the posts at one time. So to conclude and to give you some outlook, so we saw two kinds of recommender system. The first one is more like a live recommendation system for dynamic interaction, the case of OB Street. And what we did, in fact, is to create an application based on Node.js that will leverage on two NoSQL databases that are Neo4j for the graph database and MongoDB for the storage of text. So this is one kind, and the other kind is the more content-based recommender system, if you want, that is based on approximately the same stack, but is also using Redis as a cache database that will allow us to have a high availability of the recommendation, because this is a really high traffic website. And in order to finish, I will show you where we want to go. So now we are using semantic analysis on pretty large text, it's a post, but what we want to do is to exploit also the similarity between short texts, for example, the tweets or the comments in Facebook comments, and we have a PhD thesis on this subject actually. And the last part we want to explore is also to assess the quality of the recommendation, because we are doing A/B testing, but it's hard for us to sell any recommender system before doing any testing. So A/B testing is hard for us because we need to put the recommender system into production. We could do offline testing, but we don't have really the assessment of the impact of the recommendation performed. And the last point could be to use a rating from a pool of testers in order to validate all this recommendation. So thank you, and we are pleased to answer some of our questions now.